Hello, good evening students. How are you? I hope you are fine. Sorry for the delay. While listening the class, be patient, please. Magnetic flux density. It is denoted by B vector. Units are Webers per meter square or Tesla. It is defined as magnetic flux per unit area. As we know that in electrostatics, electric flux density is defined as flux per unit area. In magnetostatics, magnetic flux density is defined as magnetic flux per unit area. It is a vector quantity and expressed in Webers per meter square or Tesla. Mathematically, magnetic flux density is equal to flux per unit area. If you observe the direction, it is normal to the vector. It is the direction of the surface. I think it is clear to you. From this expression, you can also write that magnetic flux is equal to surface integral of dot product of magnetic flux density and the surface. The units of magnetic flux is Weber. Remember here, it is a surface integral. It is not a closed surface integral. It is a surface integral. Is it clear? Now, like electric flux density, d bar is equal to epsilon naught times electric field intensity in free space. Magnetic flux density is given as b bar is equal to mu naught times magnetic field intensity for free space, where mu naught is the permeability of free space, which is equal to 4 pi into 10 to the power of minus 7 Henry per meter. Is it clear? This is a very important formula. This is a very important formula. Based on this formula, there are a lot of problems. See here, they are going to give the magnetic flux density. They will ask to find out the magnetic flux. Okay, once again, if you observe that, it is defined as magnetic flux per unit area. It is a vector quantity and expressed in Webers per meter square or Tesla. This formula is very important. And the relationship between magnetic flux density and magnetic field intensity is this. Is it clear? I am not going to discuss about the problems in this video. In the next video, I am going to discuss only about the problems. Is it clear? Now coming back to the very important concept, that is second Maxwell's equations in magnetostatics. Okay, this question is also going to be asked, prove that or show that the divergence of magnetic flux density is equal to 0. Okay, now we are going to discuss about the second Maxwell's equations in magnetostatics. In an electrostatic field, the flux passing through a closed surface is the same as the charge enclosed. That is, the flux is equal to closed surface integral of d bar dot ds bar is equal to the charge enclosed. This tells about Gauss law in electrostatics, right? It is possible because it have an isolated charge. Let us consider here a positive charge. It is going to be produce some flux lines in this manner. Now I am going to consider a closed surface. Let us assume that in that closed surface there is a isolated negative charge here. Now if you observe that the flux lines coming out from the positive charge is going to be attracted by this negative charge. In this manner, in this closed surface there is some flux. Is it clear? That's why the name of this figure is given as isolated electric charge. Okay. Unlike electric flux lines, magnetic flux lines always close upon themselves as shown in this figure. This is because it is not possible to have isolated magnetic pole. Now let us consider a magnet here. It is a north pole and it is a south pole. We know that the magnetic flux lines will be like this. It will start from the north pole and it looks like it ends at south pole, but we know that internally it will complete its path from south pole to north pole. In this manner, it does not have any divergence. Is it clear? Now if you consider a closed path here, observe that if you consider a closed path here, since it is not going to be stay here, why? Because we do not have any isolated pole here. If we have an isolated pole, we can able to say that it is going to be stored in the closed surface, but it does not contain any isolated pole. Is it clear? Therefore I said that unlike electric flux lines, magnetic flux lines always close upon themselves. Is it clear? It is because it does not have any isolated magnetic pole. Is it clear? Now we know that if we want to desire to have an isolated magnetic pole, by dividing a magnetic bar successfully into two, we end up with pieces each having north and south poles as shown figure. Observe this figures carefully. This is a bar magnet. If I want to break this magnet into two pieces, then once again it creates north south poles. Okay, if you want to break it into three pieces, that means what I am trying to say here means there are no isolated pole. This figure is successive division of bar magnets. The figure says that an isolated magnetic pole does not exist. Therefore finally we can conclude that if you observe that, thus the total flux through a closed surface in a magnetic field must be zero. That means if you observe this figure, okay, the total flux inside this closed surface is equal to zero. What type of flux here? Magnetic flux. Therefore mathematically we can say that thus the total flux through a closed surface in a magnetic field must be zero. That is, the magnetic flux is equal to closed surface integral of b bar dot ds bar is equal to 0. Is it clear? This is a second Maxwell equation in integral form. This is also known as Gauss's law in magnetostatics. Remember that this is also known as Gauss's law in magnetostatics. This is a second Maxwell equation in magnetostatics in integral form. By applying divergence theorem, we know that the divergence theorem is equal to closed surface integral of b bar dot ds bar is equal to volume integral of divergence of magnetic flux density is equal to 0. Then from this we can say that the divergence of magnetic flux density is equal to 0. This is a point form or differential form. Of second Maxwell's equation in magnetostatics. This can also be asked in that manner, prove that or show that divergence of magnetic flux density is equal to 0. You have to write down the same. Okay. Now coming back to the two Maxwell's equations in magnetostatics, Maxwell's two equations in magnetostatics. If you observe that point form, integral form, remarks I have given. The first Maxwell equation means the curl of magnetic field intensity. The curl of magnetic field intensity is equal to current density. This is in point form. Now coming back to the integral form, the closed line integral of magnetic field intensity is equal to the open surface integral of current density. Okay, this first Maxwell's equations in magnetostatic is derived from Ampere's circuit law. Ampere's circuit law states that the closed line integral of h bar is equal to I enclosed, where I enclosed is equal to the surface integral of j bar dot ds bar. Is it clear? Then coming back to the second Maxwell equation, just we have derived it. The divergence of magnetic flux density is equal to 0. That means the closed surface integral of magnetic flux density is equal to 0. This is in point form, this is in integral form. Now this is derived due to there is no existence of magnetic pole. That means non-existence of magnetic pole. Is it clear? Now overallly we are going to write the four Maxwell's equations here. What we have derived, we are going to write the four Maxwell's equations here. Observe very carefully. I have once again made the table. Okay, this is a differential form or point form, integral form, remarks. Observe the first Maxwell's equation. Okay, the divergence of electric flux density is equal to volume charge density. This is in the integral form. Closed surface integral of d bar dot ds bar is equal to volume integral of rho v into dv. It is derived from Gauss's law. Now the second Maxwell's equations in point form. Okay, the curl of electric field intensity is equal to 0. That means electric field intensity, okay, the electric lines are not going to be rotate. Is it clear? They have some divergence like this. Is it clear? Then the closed line integral of electric field intensity is equal to 0. This is derived from the conservative nature of electrostatic field. If you observe the first two Maxwell's equations, these are belongs to the electrostatics. Now coming back to the third Maxwell equation, the curl of magnetic field intensity is equal to the current density. The closed line integral of magnetic field intensity is equal to the surface integral of current density. Just we have seen these two Maxwell's equations, okay, these are the two Maxwell's equations in magnetostatics, okay, and this is the third Maxwell equation, this is the fourth Maxwell equation in static fields. Observe the name of the table, Maxwell's equations for static, electric and magnetic fields. Is it clear? These are the four Maxwell's equations. Very important, these four Maxwell's equations, okay, based on these four Maxwell's equations we are going to do a lot of problems. If you observe that, if they have given the electric flux density, we can able to find out the volume charge density. If you know the volume charge density, by applying a volume integral rho v into dv using Gauss law, we can able to derive the charge enclosed, and if you know the charge enclosed, we can able to tell the flux enclosed by it. Is it clear? If we have a magnetic field intensity, we can able to find out the current density. Is it clear? These are the Maxwell's equations in static fields. Now we are going to discuss about the next topic, magnetic scalar and vector potential. Before going to discuss about the magnetic scalar and vector potential, we have to observe the two important vector identities. Observe these two important vector identities. The curl of the gradient of any scalar, the curl of gradient of any scalar must be equal to 0. If you want, you can take any scalar quantity, okay, apply the gradient, and after applying the gradient, apply a curl to the result of this, then it should be equal to 0. It must equal to 0. Now observe the second vector identity. If you observe this vector identity, the divergence of curl of any vector is equal to 0. Is it clear? Very important, these two identities. Why? Because based on these two identities, I am going to discuss the topic of magnetic scalar and vector potential. Are you clear, all of you? Okay, now I am going to discuss about the topic magnetic scalar and vector potential. Scalar magnetic potential is denoted by a letter V, where M represents magnetic. This is a potential we have seen in the electrostatic also. V is the potential, here also V is the potential, but M suffix represents the magnetic potential. It is a scalar potential, okay, it is a scalar quantity. The units of magnetic scalar potential is amperes. We will see how the units will come later. Now we have a vector magnetic potential. It is denoted by A vector. The units are Weber per meter. Very important. This topic is very important for your external point of view. This topic is very important for your external point of view. Now we are going to discuss about first scalar magnetic potential. Later we are going to discuss about vector magnetic potential. Scalar magnetic potential. Okay, remember it is not the definition. The definition is going to be discussed at last. Okay, listen carefully. Now, like electrostatic potential, now first of all we are going to discuss about scalar magnetic potential. Like electrostatic potential, E bar is equal to minus del bar into V. Magnetic scalar potential is defined in such a way that its negative gradient, that means here its is nothing but the vector magnetic potential. Is it clear? Sorry, its represents the scalar magnetic potential. Observe that its negative gradient gives the magnetic field. Okay, similar to the electrostatic potential, here also the same thing we are going to discuss about. Let us consider this is expression number 1, where Vm, we know that scalar magnetic potential in amperes. Taking curl on both sides, okay, then taking curl on both sides to the equation 1. Curl of h bar is equal to minus del bar cross del bar Vm. Is it clear, all of you? But from the vector identity just we have seen, it should equal to 0. It should equal to 0. Is it clear? This should be equal to 0. But by Ampere's circuit law, it is not equal to 0. It is equal to some current density. Is it clear? If we make Z bar is equal to 0, then it is equal to this. Then we can say that H bar is equal to minus del bar Vm. Is it clear? That means what I am trying to say here, Vm is nothing but the scalar magnetic potential. Is it clear? Scalar doesn't have a direction, it only have a magnitude. Therefore, if we want to equate this to the magnetic field, then the current should not be present in the region where we are going to equate these two. Therefore, from the basics we can say that if there is a region at which